So today we're going to be looking at transformations of log and exponential functions. We're not going to be graphing them, we're just going to be taking a look at how it affects the original graph as far as domain, range, asymptote, and x and y intercept. So first of all, reminders of what the exponential and the log domain and range are. So for an exponential, you might want to, what I do is I picture the graph in my head as I'm imagining how it got transformed. So remember, this is what an exponential function typically looks like. This would be exponential growth. The domain is all real numbers. You can take any number raised to any power. The range, however, we've got that asymptote along the x-axis. So the range is y is greater than 0. And the equation for the asymptote is y equals 0. So for the log function is an inverse of the exponential. So what that looks like is something like this, where the y-axis is the asymptote, or x equals 0 would be the equation. Domain, you can't take the log of a negative number or 0, so our domain is x is greater than 0, and the range is all real numbers. At the bottom here, I've got a chart. You can find charts for the exponential and the log functions in your book on pages 537 and 538, so I wouldn't bother copying this down. It's a bit blurry. Hopefully you can kind of decipher what's going on here. So this is the chart for the exponential function, and so if it's a vertical translation, you're adding k to the after the function, shifting it up or down. Remember, the horizontal translation is inside the parentheses. For those of you that had me earlier, you might remember my asylum example. So if it's grouped with the x, looking at the parentheses, we treat the parentheses like an asylum. And if you're in the asylum, you're not acting normal. So when we've got that minus h in the asylum, it's really shifting it to the right. If there's a plus h, or plus 1 in this case, in the asylum grouped with the x, so in this case in the exponent, it shifts it to the left. So vertical translations and vertical stretches or compressions are normal. So the next one is looking at, we take a value multiplied by the function, and it does what we think. So here 6 times the function stretches it, half times the function compresses it. The horizontal, again, it's grouped in the asylum with the x, and it does the opposite of what you think. So when we've got a fraction in the exponent, it stretches, and if we have a whole number, it compresses. So it does the opposite of what you think. And then finally, reflections. When we multiply the function by a negative, it reflects across the x-axis. So thinking about, you're making all of your y values opposite, so that reflects it across x. When you make your x values opposite, it reflects it across y. All right, so taking a look at our first example, we've got this function, and we need to describe what happened to it. So the first thing I noticed is this, our exponential is being multiplied by a negative. So again, I like to picture the graph in my head, thinking about how it's changing. So here's a sketch of e to the x. And when you're making the e to the x negative, you're making your answers negative. So it flips it across the x-axis. So that was the first thing that happened. The transformation, it reflected across x. And then the second thing is we've got this 4 here. It's a positive 4, so it shifted the graph up 4. Because another way to rewrite this function would be negative e to the x plus 4, because you can add in any order. So if that's easier to notice the vertical translation, you can rewrite it that way. Next, we're going to find the equation of the asymptote. So remember, the original equation for an exponential function is y equals 0. It's the x-axis. But when the graph gets shifted up 4, it shifts the asymptote as well. So now it's y equals 4 is the equation of the asymptote. Domain and range. Remember, for exponentials, domain is all real numbers. And that doesn't change when you transform the function. The range, taking a look at that asymptote, remember it got reflected. So when this green graph got shifted up, it's less than 4. So our new range is y is less than 4. And the asymptote and the range for the exponentials will always look similar. And finally, our y-intercept. So remember, the y-intercept is when x equals 0. So if we substitute 0 for x and evaluate, e to the 0 is 1, so we've got negative 1 plus 4. So our y-intercept would be 0, 3. Taking a look at the transformation of a log function. Again, I like to sketch, kind of picture it in my head, what it looks like. And logs, remember, look something like this. So our transformation, we are multiplying our log by 3. So we are stretching it vertically because it's outside the asylum, it's not grouped with the x. So it's a vertical stretch because it's greater than 1. And then inside the asylum, grouped with the x, is this minus 1. So it gets shifted right 1 because it's the opposite of what we think. All right, the next is the equation of the asymptote. So looking at our original log function, the asymptote is the y-axis, or x equals 0. The stretching doesn't change the asymptote, but shifting the graph right 1 will shift the asymptote right 1 as well, so it becomes x equals 1. The domain and range, domain for a log function is x is greater than 0, but now we're taking a look, we shifted everything right 1, so that shifts our domain right 1 as well. And for the log function, the domain and the equation of the asymptote will look similar. And our range is still all real numbers. That wasn't affected when we stretched it and shifted it. The last piece is the x-intercept. Remember, an x-intercept occurs when y equals 0. So we are going to set our function equal to 0 and solve for x. So the first thing that I would do is divide both sides by 3. I'm still getting 0. So notice that a stretch does not change our x-intercept. This next piece, I'm going to use the curly law. So 4 to the 0 power equals x minus 1. 4 to the 0 power is 1. And adding 1 to both sides, I get 2. So what ended up happening was my x-intercept, which was 1, 0, got shifted right with the rest of the graph. So for some of these, there are shortcuts that you can think about as you get more familiar with what a transformation does to the graph. But if you can't think about the transformation in your head, you can always solve the equation to get the x or y-intercept. One more would describe the transformation, then we're going to take a look at writing the equation of transformations. So we've got another log function. So in general, this looks like this. And now we're going to take a look at what we're doing to our natural log in this case. So here we've got a negative x. We're making all of our x values opposite. So that reflects it across the y-axis. And then the second piece is adding to what's outside the asylum, so it's a vertical translation up to. Next piece, we're going to look at the equation of the asymptote. The equation of the asymptote was x equals 0. When we reflected it, that didn't change. And when we shifted it up, it didn't change either. So the only thing that changes the equation of the asymptote is horizontal shifts. So we've still got x equals 0 for our asymptote. So the domain and range, remember the domain for log functions is linked closely to that equation of the asymptote. In this case, because we reflected it across the y, our domain is now x is less than 0. And the range is still all real numbers. So for our last piece, the x-intercept. The x-intercept occurs when y equals 0, so I can substitute 0 for f of x. Solving, I'm going to subtract 2 from both sides. Using the curly law, this one's base e, so it's e to the negative 2 equals negative x. And multiplying both sides by negative 1. So my x-intercept is negative e to the negative 2, 0. All right, so now we've got our parent function, 5 to the x power, and we're transforming it by horizontally compressing and vertically shifting. So the first thing that I'm going to do is when it's a horizontal compression, that goes in the asylum grouped with the x, and it's the opposite of what we think. It's the opposite of what it looks like. So instead of multiplying our x by half, I'm going to multiply our x by 2. And then the vertical shift is normal, so that's going to be a subtraction of 3. And we're going to get all of that data that we've gotten for our other ones. So the equation of the asymptote, remember with an exponential, it looks something like this. So the equation of the asymptote for the parent function would be y equals 0, but when we shifted it down 3, that changed the equation of the asymptote. Domain and range, domain for an exponential is all real numbers, and that does not change when you transform it. The range is linked to the asymptote, and because we didn't reflect it, it will be y is greater than negative 3. So the reflections are what will cause the y to be less than the asymptote. Next piece, we are looking at the y-intercept. So the y-intercept occurs when x equals 0. So if I substitute 0 in for x, 5 to the 0 power is 1. 1 minus 3 is negative 2. So that's the y. So there is our y-intercept. Last example, we're looking at transforming a log function. So again, thinking about the graph of the original log function, looks something like this. Reflecting across the x and the y. So reflecting across the x-axis makes the answer negative, so we multiply the whole thing by a negative. Reflecting across the y makes your x value negative. It's kind of opposite of what you think. So when you're reflecting across the y, your x value goes from a positive to a negative. When you reflect across the x, your y value goes from a positive to a negative, so that's why it's opposite. All right, and getting all of our data, equation of the asymptote, when we reflected and reflected, that doesn't change. The only thing that changes the equation of the asymptote is a horizontal shift. So our equation is still x equals 0. That would be the y-axis is the asymptote. Domain and range. The domain, because we've got the reflection across the y-axis, that changes our domain to x is less than 0 instead of x is greater than 0, but our range is still all real numbers. And finally, our x-intercept occurs when y equals 0, so setting y equal to our function, multiplying both sides by a negative, using our curly law, 3 to the 0 power. 3 to the 0 power is 1, so x would be negative 1. And if you remember, our original x-intercept is 1, 0, because log of any base of 1 equals 0, because b to the 0 power equals 1. So when we did the double reflection, it reflected it to negative 1. And I think someone needed the assignment for this one, so I want you to ignore the directions and do exactly what we were doing in this video lesson, looking for all of the different data.